This is a continuation of question 14 through 17, but I've broken it into two videos just so it's not as long. Alright, this is, before they didn't have a transformer, but now they've cranked the voltage right up, so it's high voltage in here, and they've got a transformer, step down transformer for the globe. And before connecting the circuit, the students put the power supply, this is now 20.8 voltage RMS, into an oscilloscope, so they want to see what the voltage is on the oscilloscope. So what signal would they observe on the oscilloscope? So really they're going to see a signal that looks like this. It's going to be, it's not very symmetrical. Let's try it again. And this 20.8 RMS, that means sort of the average, which is somewhere up here. That's the RMS, which is equal to 20.8. The actual top value, the peak value they're going to see, is equal to the RMS times root 2. So the peak value is going to be 20.8 times root 2, and that equals about 29 volts. So do we have the voltage peak equal to 29 volts? No, they just got 20.8 peak. So that's obviously not an answer. The other answer we could have, or the other thing they might be looking for, is from one peak to the other peak. And that is 29 this side and 29 this side. So that's the peak to peak. And that equals 29 times 2, which equals 58. And peak to peak, 58 is an answer. So there's our answer D. Right. So the globe is now operating at the values it wants to, 2 volts and 4 watts, and the transformer is an ideal transformer, step down transformer, and it's a 10 to 1. So the input coil has 1460. How many turns does the secondary coil? It's 10 to 1, so it's 1460 to something. Divide by 10. We do the same thing, divide by 10. And we get 146. Right, with the experiment set up in figure 9, what's the power loss on the transmission lines now? Show you working. Right, there's two ways we can do this. We'll put a line down the middle and we'll do one at a time. So P loss, just like we said before, equals I squared R. So we've got to work out what the current is in the power lines. Now on this side of the transformer, just like before, we have the voltage equals 2 volts, the power equals 4 watts. So if we go power equals VI, I equals power over V. We'll do the working down here. We don't know that, so we just have to leave that there. The power in the bulb equals voltage bulb, I bulb. So I bulb equals power in the bulb, divided by voltage of the bulb, which is 4 divided by 2 equals 2 amps. Just like the same as before, 2 amps. Now that 2 amps here came from another current here. Now when the voltage goes down, in this case the current goes up. So if we started with 2 amps on this side, it must have been smaller on the other side because it goes up. So it must have been 10 to 1 smaller. So I in the lines equals 0.2 amps. Okay, the current up here must have been 0.2 because it gets stepped up by 10 because the voltage goes down by 10, so the current must have gone up by 10. So to get to 2, which is what we calculated, it must have come from 0.2. And the same resistance as before, 2 lots of 2 ohms. So now we can use our formula again. P loss equals 0.2 times 4 squared, and that equals 0.16 watts. There's a second way of doing it, and that is originally we had the P loss was equal to 16 watts. Now we're using a 10-to-1 transformer. And because P loss equals I squared R, the squared's really important. Our power losses square this value. Our power losses are 10 squared less, e.g. 16 watts divided by 10 squared. 10 squared is 100, 0.16 watts. And that's what we got with the other way as well. You don't have to do both ways, but I just thought I'd show you. 0.16.